Hello and welcome. Today we will be making a sheet metal model. It's one of TooTallToby's practice models, and what's really interesting with this one is that he himself has made a tutorial on how to make it in SolidWorks and Onshape, and I think it's great to see the same model being made with different CAD software. It gives you a deeper understanding of the trade, as it were. So I think it's really interesting and important to make it in Alibre as well. But first, we need to address something, right? There you go. Look at that. So you guys are amazing, right? The viewers of this channel are amazing. I love your comments. I love the support that you're giving me, the tips that you're giving me sometimes. And let me tell you, I want to keep making videos for you guys. But you might have noticed that the sound was not one of these channel's strong points. So one of you noticed as well and stepped up and actually sent me this mic. So Stefan Uithofen, you are a true legend. Thank you so much for this. It's greatly appreciated, and you are the first holder of a new title I'm instituting for this channel, which is Stefan Uithofen. You are the first Deus Ex Machina of this channel. So there you go. First one. First Deus Ex Machina of this channel is Stefan Uithofen. So without further ado, let's step into the model. By the way, you will find the video here. It's in TooTallToby's YouTube channel. These CAD modeling challenges are amazing. I suggest you do it for your CAD system if you want to be better at 3D parametric design, basically. So it's this video. This is the name, and I've already gotten a screenshot, and we will be using this because it's a little bit easier. Now, let me first tell you how I will approach this. My approach is going to be very slightly different than TooTallToby's. I will also start designing from the center section here. A nice tip for these speed modeling challenges is you see most of the dimensions around this view, right? So basically this is how you should be starting modeling. If I was honest, I would have started modeling from here, but it's easier to start from here because you've got more information, right? You need to spend less time thinking about things. So let's go. In Alibre, as we've already talked about, to start the sheet metal part, you need to click on the sheet metal part icon. It's a different file name altogether, file type altogether. Okay, and then the first thing you do is you start with your sheet metal parameters. Now, if we go here in purple, default wall thickness 5 millimeters, default inside bend radius 5 millimeters. What does that tell us? That tells us that we need to come in here, make this 5 millimeters, make this equal to the thickness. And for if you're using Alibre and you want to do some speed modeling with sheet metal, I suggest that you change the K factor to 0.44. That's the K factor default in SolidWorks. It makes sense for a thinner sheet stock and a bend radius of around 1 to 1.5 times the thickness. We will be changing the global bend relief type to none, and we will start designing. So we will start with this shape. It's obviously a contour flange, and we can see that flange to flange on the outside we've got 80 millimeters. The height of this flange from the bottom to the top is 70 minus 30, that is 40 millimeters. And we can see that we've got 20 millimeters to the start of this bend. That means that I will need to make this flange as a separate command because I don't want to be doing the math to calculate how I should change this 70. So let's jump in. I will design on the XY plane. By the way, let me turn off my points with Alt-1. So we start here, and this will be 80 millimeters. This is going to be 14 millimeters, and this is going to be 20 millimeters. I also want to make this point the midpoint because it'll help me down the line with symmetries. And I will use, I get this warning that my sketch is not closed. That's fine, because contour flange only works with open sketches, not closed ones. And I said that this line is 18 millimeters from outside to outside, which means I need to reverse the thickness. Okay. Oh, sorry, reverse the thickness. This is very, very important. It'll create a massively wrong part if you don't pay attention, which is true with many things sheet metal. If you don't pay attention to your alignment, it will create a bad part in real life as well. So we've created this. How wide is that? That's 84 millimeters. So let's come in here and say 84 millimeters. Let's create this flange now. Yeah, let's give it 15 millimeters. Oh, so man, I hit enter. I'm supposed to do that. Well, first of all, this is at 45 degrees. Okay. Secondly, if we look at it from the side view, you can see that I intentionally made this a lot larger than I need to. And why is that? Well, we see here we've got a 70 here and we've got a 70 here, and both dimensions end, you know, at the top of this flange. What does that mean? That means that this corner needs to be exactly at the same height here. And how do you achieve that? Well, you achieve that with a sheet metal cut. And you will see that when we are using the sheet metal cut, we get a very different result than if we had used the normal cut, right? Show you what I mean. Right now, let's make that, sorry, through all. So what did the sheet metal cut? I cut this way, right? This, in this direction. So it cut here, and instead of making this face be along the direction of the cut, as would happen with a regular extrude cut, it made it perpendicular to the rest of the faces. So this can remain a 2D cut when you flat pattern it, right? And it's giving you a bit of help right there. You can see that there is some manufacturing intelligence built into the sheet metal environment. Okay, so we're done here. So next we want to be doing some chamfering. Right, there you go. So 30 millimeters and 30 degrees chamfer. And I will show you a little tip here. So if you select both of these and create an angle distance chamfer type, right? I'll make this 30 degrees. We update the preview and it is wrong. And you will see this happen in most CAD systems. I know for a fact Fusion does it. I think SolidWorks does it as well, and so on. That's a good reason to create the part in half and then mirror it like TooTallToby did. But I will take a different approach. So I want to deselect this edge for the chamfer. You can see that if I click here, it doesn't happen. So how do I do that? Well, I untoggle the preview, and now I get this 2D preview and two highlighted edges, right? And I click on this highlighted edge, and it is now removed. Okay. Untoggling the 3D preview is a great workflow for chamfer and filleting. You will see why. So let us now create the other chamfer. So I click here, 30 and 30, right? It's still in the wrong direction, but here's what I can do. I untoggle the 3D preview, and as soon as I do it, I have access to this button, right? You need to untoggle the 3D preview to have access to this button. So I untoggle it, flip, toggle, apply, done. So there you go. Now I need to create these fillets here. So I click here, select through. There you go. These are 10 millimeters, as you can see here in this broken out view, right? 10 millimeters. We've got a symmetry line here, which means that this hole is also located in the center of this little flap that we have created, and it is 10 millimeters from this top edge. So go click on this face, click on the hole tool. Quick tip: first time you click on the hole tool, it'll take a bit more time to open. So if you're in a speed modeling situation, before you enter the competition, so start your software, start the hole tool, close it back down. Next time it'll work a lot faster. So 12 millimeters here. It is a through hole. Now let's dimension from here to here. That needs to be 10 millimeters. And now we need to make this be below the center of this line segment. So what does that mean? We need to locate it onto the perpendicular bisector of that line segment. And yes, that is done by using the midpoint constraint with 3 points. So 1, 2, I've not defined the line segment, and 3, I now place this point on the perpendicular bisector. I also have a dimension here to locate it along that perpendicular bisector. So this is now fully constrained. I can hit OK, and I'm good to go. So, main piece done. Now let's click here. We can. This is interesting, right? Now let me start the measuring tool and show you. Oh, sorry. Yeah. So this is interesting, right? We pick this edge and we get a length of 60 millimeters. Now I want to make these little legs, right? And if I go here, I can see that the offset of these legs is 18 millimeters, but it is offset 18 millimeters from this edge here, right? You can also see that we have a 44 millimeters width dimension here. When you see something in parentheses, that's standard GD&T. In parentheses, it means that it is a reference value, and it is also non-important in terms of tolerance. And what that generally means is that you can find, you can derive this value from other dimensions. Indeed, we can derive this 18 here from this 44 here, and we can derive this 84 from this 84 here. Okay, that's standard GD&T. So we need to make these legs 44 millimeters. If I go here and start the flange tool, I'll click here, select through with the Alibre design tips and tricks video I did on how to select through. It's the very first one in the Alibre design tips and tricks video series. Okay, these need to be 90 degrees, right? How long should they be? Well, I have this value here of 30 millimeters, right? It is repeated over here, and that is from the bottom to the bottom of this edge flange. Okay, so it is important. First of all, let's say 30 millimeters here. Okay, so it is important to select the correct length option, because you can see that this creates different lengths. Well, in fact, the inside one was the correct one. As you can see in the icon tooltip, it measures from the inside, from the start of the inside bend radius up to the edge. That's 30 millimeters. So from this face to this face, 30 millimeters. That is correct. Oh, and as I say that, I forgot that. So we selected that edge. That edge was 60 millimeters. So it only follows that this now is also 60 millimeters, but we want it to be 44. So 60 minus 44, that is 16 divided by 2. We need to make a width offset of 8 millimeters on either side, and now it is correct. Okay, now let's make the other two flanges that fly out. Okay, and I will make them a lot larger than I need them to be intentionally, right? Let's just have a number that makes sense here, but these are a lot larger than they need to be. And again, pay attention when creating sheet metal parts, right? This is the edge I selected, right? It's highlighted, and you can see that my bend radius starts at that edge, right? It starts from that edge, so it is aligned adjacently, okay? But I know from the print that from the bottom of this face, right, this face over here, to the bottom of this face, I need to have 30 millimeters, okay? So, and that edge is already at 30 millimeters. So I need the new flange to stop the height of that edge. And how do I do that? That's the inside alignment type. Now you can see it, right? Here's the edge we selected. And okay, that is correct. By the way, this was meant to be adjacent, and it is. That's why I didn't mention it back here, but I should have actually. So let's create a cut now here. So I will now create a cut, and I will create this full round and this hole, right? And I can then locate this very easily because I know that this is symmetric, and between the two is 170 millimeters. So this hole is 170 divided by 2 millimeters from the origin, which I have placed in the center of the part. So let's go and do all that. Okay, let's start a circle with a center and 2 points. Then we need to make all of that horizontal. Okay, and then we need to make sure that this is 170 divided by 2, which is 85 millimeters. Okay, now I need this to be a geometry line, and I need a couple of lines to connect that, plus a circle here, and that was 20. That's a 20 millimeter cut. Okay, 20, and we're good to go. So I will make this cut, and then I will mirror it. So click OK, go to cut. Now that's a huge number. It's left here from before. If I was speed modeling, I'd leave it like that. If you want to reference the thickness, right, the variable is AD_thickness. But let's say that you don't remember that. You can still go inside the equation editor and say, let's type here in the search function, let's say thick. Right? I don't remember what it's called, but it's thick something. So you type thick, it brings up everything that has the word thick in it, and you say, yes, this is it, AD thickness, click OK, and now it's plugged in here. So that was a little tip, and then we will mirror this cut along the XY plane, which is the plane we started sketching on, and then we will sketch again on this plane because now we need to make this middle cut here, right? This cut over here that goes along. Now in Alibre, you can design right in this mid plane, and then perform the cut and say that you want to cut through all, because in Alibre, when you cut through all, it goes in both directions. Okay, so when cutting through all, it doesn't go only along one direction, as it does in other software, which is, I think, handy. So this is in the middle. Yeah, that 40 value, we don't need it. We just located with the origin. We do need to know the radius or diameter of this arc, and we get a value here saying that the diameter of this thing is 15 millimeters. So I click. Because it's not a full circle, Alibre is going to give me the arc. But if I hold shift and move my mouse slightly, I now get the diameter. So that is 15. And how far down should I be going? Well, I have this dimension here, which says that it's 50 millimeters from this top edge. So let's go back and say here to here, that's 50 millimeters. And now we can stop our sketch, perform a cut, go through all, click OK. And guys, that's it. That's the part done. Now, it's always a good idea to click on flat pattern, right? If it creates the flat pattern, it flattens it, means that, well, at least it's a sheet metal part, right? No major mistakes have happened. And now we should check what the mass is. But, you know, to check what the mass is, we need to apply a material, right? So two ways to do it. You either right click on this icon, select from material library, so on, or you can just click here. Now this is supposed to be steel, right? So here's another tip. In Alibre's library, in the steel folder, there is no steel that has the same density specified in TooTallToby's competition, right? So TooTallToby's competitions call for a 7,800 kilograms per square meter density for steel, and none of the steels here have it. So how do you go about creating it? You select one of these, you copy it, and then you come up here, right click, new library, which I've already done. Don't ask about the name. And then you right click on this library and paste into folder. Oh, sorry for that. As soon as you paste into the folder and you click on the material you've pasted, you can change the name, density, hardness, whatever. It is now an editable material. So while I have it selected, I just click apply. And now the material has been applied. You can see it here. And now I can check out the physical properties, calculate, and I get a mass of 645.2074 grams. Now, how do I know if this is correct? Well, that's how TooTallToby's practice models work. You go back into the model, right? And if you see here in the chapters, you go all the way to the end and you get a chapter here. It's not very easy to read, but it's called answer revealed. So you just click here, 645 grams with a tolerance of plus or minus 2 grams. And of course, we are completely within tolerance. So we won because we finished first, because there wasn't anybody else modeling. But I guess that's one way to finish first. Run on your own. Okay, so we saw some really cool tips here. We saw that we should be paying attention always because mistakes cost a lot in sheet metal. We saw how the sheet metal cut works slightly differently to the actual regular extrude cut. It's good practice if you make this model on your own. It's a great sheet metal practice model, actually. And if you do make it on your own, perform this cut here, both with the sheet metal cut and the regular cut. You will see the difference. It's very, very distinctive. It'll be nice to have that as an image in your head, right? So that's it. If you like this video and you want more like it, please subscribe, hit the like button. It'll help me a lot. And if you didn't like it, hit the dislike button because I still want to know if you didn't like it. And I hope I see you in the next one.